Yes, yes. Perhaps at the beginning, at the very beginning, I didn't know that Khanin originated from his parents or grandparents in Russia. I was mistaken by his name, Khanin, and I thought that he was an Indian. Also, the color of his skin was consistent because he was spent a lot of time in the sun. So for quite a while, he was my favorite Indian. Not quite true. Never mind. All right. So let me start now. And so the subject encompasses roughly 5 centuries. So it goes from Leonardo da Vinci and much more recently Andrei Kolmogorov and Giorgio Parisi and a few others. By the way, Giorgio Parisi was one of the people who got the Nobel Prize last year, together with Manati and Hasselmann. And we have worked a lot together, not just with Khanin, also with Parisi. Yeah. Okay. So now let me see. That should work. Great. Yeah. And the problem is that one has to lift the height. Yeah. So this is about Leonardo and turbulence. And a very similar aspect of turbulent motion in air or water has interested the poet and philosopher Lucretius at the time of the ancient Romans. But that is a completely different matter. So let us start significantly later, about 5 centuries ago, with Leonardo da Vinci, who studied the decay of eddies in the rivers. This is an example. This was shown to you yesterday, I believe. And what is interesting is that Leonardo called such flow turbulence, a name used before for random motion of leaves pushed by wind. It's very different. The question is, was Leonardo actually the originator of the modern word turbulence? So with Giorgio Parisi, we discussed that after the Rome conference in Rome in early October. And Giorgio Parisi pointed out that a full list of, nearly full list of all the books that Leonardo had been reading was with him when he died in 1519 in France. And that list is available. And most of the books are at the Academy de Licei, the Academy of Linguists, the first ever academy, which disappeared after a while and reappeared. So the problem has been started to try to read most of the books that were available to Leonardo when he started getting interested in what we call turbulence. Yeah, and see if anybody before to Leonardo has used the word. We don't know, and that will be an interesting challenge. So let me Now, this is particularly interesting. Excuse me, this is really not very good for me because I had some surgery recently and yeah, this is better because then I don't have to lift. This is, by the way, why the sound of my voice is strange, because I was intubated for 5 hours of surgery. Everything went superbly, except it will take another few weeks until my voice becomes normal. Yeah, that is much better. So, so let me introduce you to Leonardo and what was later called Codice Atlantico. For this, I have to take a lesser figure whose name is Pompeo Leone. Please note that he was born in 1533, which was some 20 years after the death of Leonardo. And eventually he collected a number of manuscripts of Leonardo and organized them with a criterion of his own. The result was called Codice Atlantico. Now, rather close to the beginning of the Codice. It's a huge thing, you know. It is more than 1,000 pages. And it was organized by the Pompeo Leone in a completely stochastic way. It took many centuries until people were able to find the correct organization. I'll come to that. So in this big thing, we have the full volume here at the Observatoire de Nice. This is a huge thing. And something suggesting that this was early work of Leonardo. That's wrong. We'll come to that. And according to the organization, the work would have been done around 1480. And the first stay of Leonardo and that's very strange. It took me tens of years to realize this is wrong. Here's the true answer. Let me, yeah. Now the accurate dating of the Codice Atlantico was discovered only recently. It was done by Augusto Marinoni, who died in 1997. And he was a great specialist of Leonardo da Vinci. All his work and all his writing and the changes of his manuscript in the course of time, etc. So he was able to date all the text and figures of Leonardo. And lo and behold, the most interesting thing for me, which is the decay of turbulence, wasn't at all produced around 1480, but in 1505 roughly. And that was around the second stay of Leonardo in Florence. As you know, he was born very close to Florence, and he left it after a number of years, roughly 30, went to Milan, etc., 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 then returned to Florence, eventually ended up in France. So now, let me see here. Yes. What is interesting, 1505 roughly, according to Marinoni's guesses, that is roughly 1 year after Leonardo was busy planning to divert the course of the Arno River, which flows through Florence, but also Pisa into the Mediterranean. Why did he want to do that? At that time, many cities in what is now Italy were at war. And it was important for the people of Florence to make sure that the river does not end up in Pisa. So there was a huge study of how to divert. Eventually, the cost was fantastically high, so they gave up. However, this was also an experimental text. And although Leonardo at that time was 50, which is a very advanced age at that time, he typically would go inside the Arno River, dive there, and look at things and measure the way the eddies were decreasing. But let me turn to the next one. And that's it. Now, Leonardo, as most of you know, was left-handed, and he wrote with the left hand, and he found it convenient to do it this way and not that way. So that is the original writing of Leonardo. It's a little bit difficult, but if you turn it up with a computer, that's trivial. Look, la turbulenza, and so on. Everything becomes clear. So what is written here in ancient Italian, but which is very close to modern Italian. I'm not going to read to you the Italian, but I'm giving you the English, a good translation, where the turbulence, where the turbulence of water is generated, where the turbulence of water maintains for long, where the turbulence of water comes to rest. That was the first attempt to study the decay of turbulence. And at that time, the mathematics, logarithm, exponentials have not been invented. So Leonardo, who was fairly good at mathematics, he had to just to say that it maintains for long. Probably that means it is not, in modern language, it wasn't decaying exponentially. But the study of Leonardo was not just with experiment, but also by diving into the Arno and looking at with these special glasses that he divided. So he was able to look from out, to look at the edges from above and see if they were rotating fast or more slowly, etc. So after this fantastic work of Leonardo, 5 centuries ago, 4.5 centuries actually ago, nothing much happened until these very recent people, Khanin and Kolmogorov, came up. So what did they do? It's a long time, 4 centuries more. So 1938, that was yesterday, on the time scale of Leonardo. For most of us, this 1938 means a very long time ago, but of course, be prepared to these things. Turbulence is probably one of the most ancient turbulent stuff which is still not solved. So it's a big problem. Now, Khanin had a certain theory which was in part triggered by Taylor. But and then Kolmogorov read the paper by Khanin. 3 years later, he found it as a mistake. I mean, a completely stupid mistake. Like if I write A plus B is C plus D, and then you can change it. If you forget to say angel sign, something like that. So Kolmogorov corrected it. Did he get the right answer? No. Kolmogorov's mistake was even bigger, because at that time there was a Russian whose name was Loyansky, who had thought that he had found a new invariant of the equations of Euler and Navier-Stokes. And Kolmogorov was using it. And he found that the law of decay of the energy and so on was T to the minus 10/7. That was wrong. Our law perhaps, but not this particular part. And but at that time, Loyansky's derivation looks fine. Wait. There were other people. Kolmogorov did his work in 1941. And it took a few years, 1954, until 2 great scientists, Proudman and Reed. Proudman is the son of an even more famous Proudman, British. And Reed is an American who went to Cambridge to study with Proudman. And both of them are now dead, but Reed only rather recently. And they found that the derivation of Kolmogorov of 1941 was wrong. For a while, everybody said, "Ah, that's very interesting." And then everybody changed their minds. Now I am going to explain to you that Proudman and Reed derivation is correct. This is perhaps the first time this is announced in public. And for this, at one point, I will use the graphs that were written on the blackboard. Yeah. So let me see. Is there this looks okay. These are Feynman graphs roughly. So let me just put here we have a K, J, wave number P and Q. Now let us assume that P and Q are fairly large, and by conservation, K has to be P plus Q if they are fairly large but nearly opposite. That can be much smaller than this one. And the question is that has been understood since Proudman and Reed, the non-local interactions, be they expressed in physical space or in Fourier space, highly non-local. So you have, it's convenient to do it in wave number space, but that's the same. So you have P and Q that are large. It means small scales. They interact and you get a tiny little K, which means a large scale. And you want to find what is happening and how the flow is driven up or down by this. And there is a simple way. Suppose the flow initially at time t equals 0 is Gaussian. Of course, because the equations are nonlinear, it will not stay Gaussian. But at short times, it will be close to Gaussian. And if it's Gaussian, you can calculate all kinds of moments that were presented to you yesterday. And you can find what is going on, and actually it is quite simple. Here, you have a K, another K. K times K is K squared. And then you have to take into account the geometry in 3 dimensions. The volume element goes like K squared. K squared multiplied by K is K to the 4th. That is what Proudman and Reed found, that the acceleration goes like K to the 4th. And although they used the so-called quasi-normal approximation, quasi-normal means pretending that the solution is still Gaussian. It isn't, for short times, it is very close to Gaussian. Of course, after that, it is different. But it is easy to show that when some Japanese fellow in the 60s found that the quasi-normal approximation apparently produces rubbish because the energy event can become negative, which is of course nonsense. However, they become negative. That's not a very small k, large, rather large k. That's not relevant here. So, I mean, I could explain the thing in more detail, but then that would require several lectures. I can tell you that to leading order, the Proudman and Reed thing is correct. That means that they have indeed found a mistake in Kolmogorov. So we have these two guys, Khanin and Kolmogorov. Look, Einstein also occasionally makes mistakes. There is even some document, all the Talmud and so on, it is claimed that God occasionally makes mistakes. So what can you do? No, it's the wrong. Much better. Yeah. So now we're going from Kolmogorov to intermittency. The subject has already been handled yesterday, so I will go quickly. Kolmogorov's 1941 theory was a completely self-similar picture. Very interesting, with many practical applications, not completely wrong. Interesting, but not quite right. And so in a paper that was written by Sülem, Nelken, and myself on the so-called beta model in 1978, we were contrasting Kolmogorov's 1941 and fractal models. The fractal thing was actually also invented by Kolmogorov when he found that the experiments carried out at his lab and nearby, near Moscow, were showing that this thing is not exactly self-similar. So the complete theory was developed by Mandelbrot. And it's useful to show it little pictures. This is a self-similar picture, and this is a fractal one, where the large things are the same here and there, but then they become rarer and rarer, and most of the thing, there is nothing. So these are fractal models, and at first, nobody could think, I mean, going from a normal thing to a fractal is a bit exotic. Having more than one fractal thing didn't occur to any of us at first. So the beta model had a single fractal dimension. Aha. Let me see. Yeah. Then the thing started from experimental work. The experimental work was done by Anselme, Gagne, Hopfinger, and Antonia. And it was published in 1984, but preliminary the results were transmitted to me and then to Parisi in 83. There was a summer school in Italy there. And it was very strange. We could not understand what was going on by having a single fractal dimension. We were forced to do something which at first I hated, multi-fractals. And fortunately, that seems to be the truth. And so that means that you have expansions and fractal dimension which continuously change with that is a very strange thing. It's so strange that my great admiration for Giorgio Parisi, I thought he must be right, even if I don't understand it. But wait. Then, whoops. A few years later, we understood that multi-fractality is just an implementation of something that had been invented several years before by Kramer, a Swedish probabilist who was a great friend of Paul Lévy. Actually, he wrote also in French. I have no problem understanding French. And actually, I'm born in France. So the essence here, I could put in here 30 pages, but I want to concentrate on just one few things. You take the so-called structure function, the velocity increment over a certain distance L. It's convenient to take an absolute value that is not too important. And when you average, and what you find is the so-called structure function, which this is the very notation of Kolmogorov. He called them structure functions. And then if you assume that you can evaluate all this thing by a saddle point evaluation, it's quite simple to find that the structure function of order P has an exponent which is given by this thing. That's just a Legendre transform. It's a simple Legendre transform, something that was known for quite a long time. And so then we realized after a couple of years had passed that the machinery of multi-fractality had actually been developed by Kramer, not for turbulence, but for finance. But it's the same machinery. And what was very crucial that, you know, when you add a lot of random variables, independent and so on, then you easily get Gaussian laws. But if you go to large deviations, the Gaussian law doesn't work. You have other laws. And they were all studied by Kramer. He was a great man. Kolmogorov, of course, eventually learned about all this thing And but that, yeah, that was after he had finished the work that was reported before. So what is interesting here is that when you look at the whole body of things that can be handled by grammar, not just in finance, in turbulence, in statistical mechanics, entropy is a crucial thing which connects with Kolmogorov, with large deviations. That was realized rather recently. So now let me also point out, yeah, there is a paradox. Multi-fractal analysis has had many children now in all kinds of fields. But in turbulence itself, they are almost all illegitimate children. They are not derived by kosher theorems. Because in turbulence with Euler and Navier-Stokes in 3 dimensions, we don't have the right theorems. We don't even know if blow-up is happening after a finite time or not, and things like that. So it's a bit embarrassing. So multi-fractality was born in turbulence, but we have no rigorous theorems there. So how to develop it? If one is really interested in turbulence. The idea is there may be models which have a strong hydrodynamical flavor, but which are not as difficult to treat mathematically as full turbulence. What comes rather quickly to mind is the Burger's equation, the one-dimensional Burger's equation. I will show it to you in a moment. But there is a difficulty. For anybody who has studied the Burger's equation, you know it's full of shocks. That's well understood. And shocks can accumulate sometimes, but it's not too difficult to show that it is not multifractal. It has a single fractal dimension. It's not the right thing. Let me see. Yeah. Finally, the work, of course, all the work that was being done in the last 3 years, most of which were under the, how should I say, the imprint of COVID, which has good things. There were many conferences here held virtually. This one is only has so many word virtual. It's much better to see the real people. Well, so you see, yeah. So what I'm reporting now has been done in very close contact with this guy, whoops, sorry, Konstantin, Rahul, Pandit, whoops, and where is Deepankar? Yeah, yes. We were working together on a daily basis, sometimes several times a day. We were working like that. And we made some progress. Not everything is solved, but it's interesting. So let me just remind you, of course, what the Burger's equation is. Everybody knows it. It's just a kind of Navier-Stokes equation brought down to dimension 1 plus time, of course. Yeah. What is very, very interesting in the Burger's equation is that you have in the limit of vanishing viscosity, you have a fantastic thing. One does not know who proved it, because Burger's claims that Hopf and Cole proved it. But I looked at their paper, they didn't really prove it. I suspect that Burger's was a very modest man. And so we shall just give it a name and we shall not call it Hopf. We shall not call it Cole or Burger's, just a Max principle. The Max principle is that when you take the potential, the velocity has a potential, so V is minus gradient of a potential phi. Then in the limit of vanishing the viscosity, it's been known now for quite a long time, that the potential at time t can be expressed explicitly in terms of the initial potential and a nice parabolic term. Yeah. That has no parallel for the Navier-Stokes, unfortunately. This is very useful. And the problem when we realize that multi-fractality perhaps can be studied with Burger's equation, I immediately thought about the small scales of Burger's. That doesn't work. Because they are, one gets devil staircases and things like that, but they have a single dimension. But this is not multifractal. So what to do? It took many years until we realized the Burger's equation, if one studies not the small scales, but the very large scales, there is some good reason to believe that the things that are multifractal. Not the proof yet. And the example of what one can do. Now this is semi-serious mathematics on the Burger's equation. If the initial data for the potential is, sorry, is of Brownian type, what do we mean by that? Know that Brownian curve in space means roughly that the increment between 2 points squared goes like the absolute value of the distance, completely trivial thing. But that has a generalization which is known by the name of Hurst standard Brownian as the exponent 1/2, but you can extend it to any exponent which is strictly between 0 and 1. These are only the standard Brownian is Markov. The rest is more difficult, but good progress have been made recently. And what is happening is that if one uses the Max formula and plots the velocity for any h between 0 and 1 gets this kind of thing. And when time changes, the whole thing evolved in a self-similar way. It's fractal sometimes, but this is not multifractal. So what to do? I need this one. Yeah. First of all, we can, if you revisit the case of Hurst with a single exponent h, which is not 1/2, then the theory works rather nicely. And what you find is that the whole thing evolves self-similarly, and the energy K goes by T to some negative power, which depends on H. That's boring. That's not what we want. That's it. Now, we realized that having a single H is not enough. You have to have intervals in the initial data where H is basically constant and then changes very rapidly to another H, to another H, and so on. The simplest model of it, we tried with all kinds of things, is the hyperbolic tangent. You know, the hyperbolic tangent goes to limits there, and if the interval where it changes is small, it is almost constant. So here is an example of what the initial data are. They are not discontinuous. They're just rather changing from a certain H1 to an H2, etc. And oops. So that will be the conclusions. The conclusion is that the best wind tunnel data obtained on facilities in France and elsewhere is that you cannot describe turbulence with a single fractal thing. And as you probably know, multi-fractality has found a number of applications which sometimes are not too far from turbulence, but not really turbulence, chaotic dynamical systems. The other one has real theorems, but that's not turbulence. So now, here is where we stand now. He, I mean, who is he? Who is the we? All the people who are working on it, the four in this room, and a few more who are quite curious to see what we will find. The conclusion at the moment is that proving things rigorously may take many years. Why? Sinai, who is not exactly stupid, was able to use the result of Uriel, and myself. There is a devil's staircase to prove theorems, but that was for the case where H is 1/2, Markov. And H is not 1/2, it's very difficult. A Russian specialist who is a friend of Sinai, and of Sinai and of myself, Mao-Chan, spent 15 years investigating H not 1/2, and he succeeded. But gosh, that was real tough. So proving real theorems is difficult, but what we do hope is that by heuristic arguments, clean simulations, and semi-hand-waving arguments, one can get some idea what's happening over a time scale of 1 year, not 15 years. It may take 15 years until the real theorem is proven, but you have to be patient, and COVID helps in those cases. It's not an obstacle. That's all I have to say.